Okay, thanks so much for coming out tonight. Can you all hear me okay? Is the mic good? Okay.
Not that good.
Not that good? Is it not that good?
That's better.
Is that better?
I think you just need to hold it close.
Okay. I'll do my stand-up routine this way. I'm Dean Wampler. I joined Anyscale in November, so I didn't make the first two meetups. This is the third. How many of you have been to all three meetups? Okay, we're going to give out perfect attendance pins at the end, if you stick around. How many of you are here for the first time? Oh, great. Okay, that's really exciting. If you want to complain, you can send me email or Twitter here. Just in case you're new to Ray, just a quick, what is it kind of thing. So Ray is a system, basically a library really, for distributing Python applications across a cluster, with minimal pain, minimal tears. We all know that Python has limitations about concurrency and so forth. And Ray is designed to make it really easy to break past those barriers and scale arbitrarily far as you need to for very high performance, high compute kind of jobs like reinforcement learning, hyperparameter tuning, that kind of stuff. And so some of the libraries that have been written on top of Ray that are part of the Ray package include RLlib for reinforcement learning, Tune for hyperparameter tuning. Actually, how many of you are playing around with RLlib already? How about Tune? How about Ray itself? Maybe none of the, okay. How many of you don't even know how to spell Ray? Okay. All right, good. There's a new one that we're going to hear about tonight called Serve. And there's a project at Berkeley that's a data frame on Ray kind of project called Modin. And then there's a bunch of other things people have been working on, and you'll hear about some of those tonight. If you'd like to get involved, and I'm going to put these slides somewhere and post a comment to the meetup so you don't have to, memorize this list. We've got a Slack channel, Google group, homepage. You can go, download the code on GitHub, fork it, whatever. Anyscale is the company that is, basically developing Ray now. It spun out of Berkeley. You can tweet storm the interwebs, a couple of Twitter accounts. But if you don't know anything else after tonight, make sure you register for Ray Summit. That's coming up May 27 and 28. The call for proposals closes tomorrow, but if you want to put in something and can't get it in, then just, once again, spam me on the internet. And it's really cheap. Like right now, it's only $350 for a day of tutorials and a day of keynotes and talks. And that, I think, lasts for another 2 months or so, that early bird price. But you can see some of the keynoters we've got already. We're really proud of some of the people we've been able to get out. And I hope you'll join us. It'll be downtown here in San Francisco at the Hyatt, I guess. Okay, so here's the schedule tonight. Actually, first, while I think about it, just some administrivia. If you need the restroom, they're down the hall here. There's signs on the pillars. Let's keep it informal. If you feel pangs of hunger or pangs of thirst, you know where to go. Feel free to do that. Although we will take sort of quick breaks between each talk to set each one up, so you can hold off if you want. But anyway, I hope you all just did networking, pizza, and drinks in that order. Right now, we're going to have a talk by Edward Oakes. He's one of the engineers from Anyscale, and he's going to talk about some of the cool things we've done to re-architect Ray's internals for much better performance. Then Michelangelo Corporale from Lumenta is going to talk to us about how they're using Ray to scale experiments. Eddie Palencia from Microsoft is going to talk about what they're doing with Ray and RLlib. Then Simon Moe from Anyscale is going to talk about this new Ray serve module, and then general carousing and so forth afterwards. Okay, I think that's all I've got. So yes, that's it. So if Edward would come up here, we'll get started with the next talk.
Okay, can everybody hear me? People in the back? Yeah? Okay, awesome. Yeah, so my name is Edward Oakes. I'm a software engineer at Anyscale, where I primarily work on the Ray core. So one of the big things we've been working on lately is basically this re-architecture to improve the performance of scheduling task submissions in Ray. This is primarily collaboration with Eric and Stephanie, who are also both working at Anyscale as well as doing their PhDs at Berkeley. But of course, this also couldn't be possible without all the other people at Anyscale as well as open source contributors. So the motivation for this, you might be asking, like, why do we care about having really high performance for the scheduler? And the answer is really, well, we see users coming to the Ray GitHub with these issues where they're indicating that they're using Ray alongside these low-level queuing libraries like multiprocessing. So they're using Ray to basically orchestrate the high-level structure of their program, but then they run into performance issues where Ray isn't fast enough, and they have to reach for things like multiprocessing queues and pools in order to get the performance they want on a single node. Clearly, this isn't what we want. Like, Ray is advertised as being really high performance and having low latency, so this is something we need to address. So here's an example program of where you run into issues. So this is a really simple program where we just have this single remote task that's called process, and it's just going to take in some data and do a really lightweight computation over it. So if you schedule a ton of these process remote tasks, say like 10,000 of them, and then try to get the results in a single process, this is like a really simple, embarrassingly parallel workload, so it should be really fast. But because Ray offers all these offers a really expressive API and set of features, the overhead for this is actually much higher than a simple low-level library like multiprocessing is. So the goal with Ray 0.8 and this effort is to make Ray as fast as using these lower-level libraries directly in situations like this where we have sort of simple patterns and we should be really fast. So to understand what we did to achieve this, you have to understand a little bit about sort of the status quo. So prior to this effort, basically every time you submitted a task, the task state was written to what we call a global control store, which is just a centralized metadata storage. So let's run through what it looks like when you submit a task. So in this example, we're just going to be submitting a single task from this worker process over to the other one on the right. So the first thing that happens is we submit the task to the local Raylet, which just manages the local machine. The Raylet then records lineage, which is just information about where the task came from, like what objects were input to it and where it was ran. And then also the state of its execution into that GCS, or Global Control Store process. This is in charge of storing that metadata for any subsequent lookups by any other process in the cluster. Then the Raylet forwards the task to another worker process. This might be running on the same machine, or it's running on a remote machine. Then this worker communicates with another process called the object store in order to get any arguments that it has, and then also once it finishes processing to store its results. And then this object store process also communicates with the Raylet. So we have this really complicated set of things that's happening just so that we can maintain basically global state so that we can support this expressive API and also be tolerant to failures. Oh, and then at the very end, this initial worker process wants to get the result, and it also has to communicate with two of these centralized processes. So clearly you can see how this is much more overhead than we need for that really simple example that I showed before. So I'll be talking about basically how we address this to remove some of these centralized bottlenecks. The challenge here is we still want to preserve the generality. Like, one of the great things about Ray is we have this really expressive API. We automatically recover from failures. You can specify resources, and it handles scheduling across the cluster, et cetera. So we don't want to sacrifice any of that generality just to get performance for these simple cases. Yeah, and here's some of the expressive parts of our API. So these low-level libraries that people are reaching for that have higher performance are basically don't support these features, meaning they're sacrificing generality for performance. And prior to this effort, Ray was maybe somewhere over here, where we were sacrificing some performance. We still did relatively well in exchange for having really high generality because we support all of these really nice features. And with Ray 0.8, we're trying to push up and to the right and sort of the ideal part of this chart. So the high-level approach that we took to address this is basically recognizing that we can have like multiple paths through the code. So this is like something that happens, or this is a really common optimization technique, is you take the fast path and make it as fast as you possibly can, and then fall back to a slow path when you need to. So in our case, the goal is to make this fast path for task submission as fast as just doing a single RPC. And we have 3 key optimizations that let us basically achieve this. And I'll talk about each one of these in turn, so don't worry if you don't understand what they mean out of context here. So the first of these optimizations is co-locating task state with the worker that submitted a task. So the key insight here is that actually in most of the cases, including the case that I had flashed earlier with this really simple program, actually the only process in the system that cares about the submitted task state is the one that submitted it. So what this means is that instead of having to update all of this global state and have these centralized global bottlenecks, we can actually just keep the state at the worker that submitted the task. So here, this is the diagram that I went through earlier. And what it looks like when we collocate task state at the worker that submitted it is instead of actually submitting the task to the Raylet, what we're going to do now is just get a lease for a worker in the cluster. So this goes through all of the same like scheduling mechanisms, but instead of actually submitting the task through the Raylet, we're just asking for a lease for a worker, which means that we're the only process in the system that's allowed to submit tasks for a certain period of time. Then this worker directly submits the task to the leased worker. So we still have the same scheduling guarantees, but we're just communicating directly between the worker processes. And then instead of storing any metadata in this global control store about the task lineage and execution state, we're just keeping it at the worker that submitted the task. So what this means is we now have this faster scheduling where we don't have to communicate with the global control store at all on the task submission path. So we've gotten rid of one of these central bottlenecks. And one of the obvious questions is, do we lose anything by doing this, right? So now we're basically, by collocating the task state, we're now fate sharing that state with the worker that submitted a process. So that means if that worker goes down, then we lose all of the metadata about the task that it submitted. So we may have to go through like more task submissions if we need to recover the result. But really in practice, this is not a big deal, right? Failure is already a slow path because we have to resubmit all of these tasks. We have to go to this central control store. So it's already a slow path, and it also shouldn't be the common path. And then there's this other question, well, what if other workers need to access that state? Well, it turns out that this is actually pretty similar to what we had before, except instead of looking it up in the global storage, you just ask the worker that holds the state. OK, so moving on to the second optimization we made. So now that we can submit tasks directly to other workers, so yeah, I showed how that removes some of the central bottlenecks, but we still have to go through this centralized or somewhat centralized scheduling decision-making process when we lease a worker from the Raylet. However, notice that we don't actually need to do this for every single task we submit. We can reuse these scheduling decisions, which is hinted at a little bit by the fact that this is a lease. So what we can do is when we get a lease for a worker, instead of just submitting a single task, we can keep the lease and continue submitting tasks. However, notice that in order to maintain generality or to maintain correctness with the scheduling, this work or the subsequent tasks that we're submitting have to have the same what we call like scheduling shape. So that means it has the same dependencies and has to have the same resources. So if I if I get a lease for a worker for a single CPU task, and then I try to submit a 2 CPU task on that same worker, well, obviously that breaks the scheduling logic because the scheduler didn't know that you were going to use that for 2 CPUs. So we can't do that. We can only do this caching when the scheduling shape is exactly the same. So now, instead of having to go through this get worker lease every time, on the fast path when we're submitting many tasks that have the same scheduling shape, we can actually just keep the lease for that and submit the task directly, which means now we've removed another centralized bottleneck, and the only one remaining is going through this object store. So the final one will be addressing that problem. And the key insight here is that if an object is passed by value, and I'll explain what by value means in just a second, then we can just inline it in the task instead of having to go through this object store, and we don't actually externalize its ID at all, meaning the ID, because we know the ID won't be used in sort of these like complex ways like passing IDs between processes, we don't have to worry about updating the global metadata about the ID. So if we look at these two simple examples, the first one here, we're submitting a first remote function, and then we're taking the result from that function and submitting it into a second. So in this case, G does not actually get a reference to XID. It only gets a reference to the underlying value from X. So this means that we don't have to worry about having XID in the global metadata store because we know that this can still only be used at at the current process here. So we say that the XID does not escape the current process. We don't have to worry about the caching issue that the state is only at this process because it can't be used anywhere else. In contrast, if we were to pass XID by reference, so in this case, G does have reference to the actual ID, and it could forward it to other tasks and so on. In this case, we would say that XID escaped this process. So in this case, we do have to go through like entering its metadata into the centralized storage. So if we revisit what the task submission workflow looks like now, instead of going through the object store for everything, we're only doing it when we have objects that escape, like I talked about in the previous slide. And then also for large objects, because for large objects, the object store is like really optimized for large object transfer. So that turns out to outweigh the downside of going through like the centralized bottleneck. So now you'll notice that we've basically achieved what I set out to do in the beginning of the talk, which is we want this fast path to just look like a single RPC between two processes. So if you think back to the example we had, where we're submitting the same task just 10,000 times in a row, now all we have to do, instead of this really complex protocol for every one of those task submissions, is just basically do that protocol once, and then the subsequent requests are just a single RPC between two processes. So what does this look like in performance? So on the bottom, or sorry, on the top, you can see raise 0.7. So that's before any of these optimizations. You can see that we were just under like 300 microsecond latency for doing a call between two actors. And you can see gRPC, which can be seen as like the lower bound is around like 200 microseconds. And the really interesting thing is now in raise 0.8, we do better than only gRPC. So this might look like black magic because we use gRPC underneath. But this is actually just because in Ray we're using the like more optimized C++ gRPC library, and this is using the Python gRPC library. So if you plot the C++ latency, it ends up being like just slightly under what we have in Ray. So what does this mean at sort of a higher level? So here we have three conditions, and we're just plotting the number of tasks per second that we can submit and get the response for. So on the left, we have tasks with a single submitter. Here we have tasks with multiple submitters. And then here we have many actors submitting to many other actors. So in Ray 0.7, you can see all of them hovered around 6,000 tasks per second because of these centralized bottlenecks. And now in Ray 0.8, we do substantially better. So we do between like 3x and something like 8x faster for actor calls. And we also have better scaling. So previously, even if the cluster was very large and you had many actors that were invoking methods on many actors, we couldn't scale past this around 10,000 tasks per second mark because of the centralized bottlenecks. But now you can see, because we have them communicating directly with each other, it scales pretty much linearly with the size of the cluster. And finally, so oftentimes when you see sort of like performance work, you publish like micro benchmarks and they look really good. And then when you actually run real applications, it sort of doesn't matter, or maybe you only see like negligible impact. But actually, when we were doing the working on some benchmarks during the release process, we saw that in RLib, which is something a lot of you are familiar with, reinforcement learning on top of Ray, between 0.7, which is plotted here, and 0.8, we actually saw like very substantial improvements in performance. So this is not just us optimizing away sort of like a small toy case. It actually has like real impact on applications. Yeah, so in conclusion, I went over 3 key optimizations that we worked on for this latest release. And basically, the outcome is we've significantly improved performance for a lot of applications without impacting the generality of the system. And then it's also the groundwork for the next major thing we're going to work on, which is reference counting of object IDs, which is basically the goal is basically to make sure that anytime you have an object ID in the system, you know that that object is still in memory somewhere. So that'll be a focus in the upcoming months, and I'll take any questions that you might have about this.
A question for the video.
Oh, yeah.
What's your definition of a large object?
He asked, what's my definition of a large object? That's a really good question. Do you mean like when do we spill to the object store? So we did benchmarks to determine when to do it, and think it's 100 kilobytes. So it's still relatively small, actually. That's basically, yeah, just the point at which like optimizing the throughput is more important than the latency. Yeah, thanks. Oh, I didn't do it. Yeah.
I have another one. When does that linear scaling stop? Or is it always going to linearly scale no matter how big the work is?
Yeah, the question is, when does the linear scaling of actor-to-actor communication stop? That's a great question. It shouldn't, yeah, I don't, there's no reason why it should stop, actually. I mean, there's no centralized code for that.
When you get the CPU bottleneck, right? It's like CPU bottleneck, serialization, gRPC.
Yeah, I mean, you have the same bottlenecks as gRPC, sure. Yeah. Okay, I think that's it.
All right.
Oh, one more question?
So when you say leasing, is it leasing on time for that remote block?
Oh, yeah, so he asked, what do I mean when I say leasing? Yeah, so the lease is basically when we request a worker, we get it for like a maximum predefined time. I think in the code it's like 500 milliseconds or something like that. So while that period is up, if you have more tasks that can be scheduled on that worker, you'll continue to submit them. And then once the queue is empty or that time is up, then the lease expires and it gets returned to the scheduler.
If it's not finished within that time, like, because it seems like as a user, you don't control that.
Oh, right, yeah. So if the task doesn't finish in that time period, then once the task finishes, it'll be returned.
Okay.
Yeah. Yeah.
Then I have a question about the decision to go between the fast pass and the slow pass. Is that only based on the object size, or do you have other tipping points?
Yeah, he asked if the decision to go between fast path and slow path is only based on object size. Yeah, so right now it's the only performance consideration is object size. There are some other considerations, like if you get the result of a task and then you want to share it in other places in the cluster. So if it like escapes by what I said earlier, then we put it in the shared object store, because then you need to have it in like global storage so anyone can access it. But the size is the only performance decision. Yeah.
What about if you have like specific resources on a given worker that you may not want to give it leases because some other task need resources? This kind of use cases.
Oh, sure. Yeah, I don't think, yeah, that sounds like kind of a complex example. I'd be happy to talk about it offline, but I think it'll be hard to figure that out here. Okay, last question. Yep.
I'm wondering if there's a way to like profile code and figure out which path it's running on. So like if you're writing code, it seems like it would be hard without some tool like that to know if you're actually optimizing the path or if
Yeah.
you're missing it in key parts, stuff like that.
Yeah, that's a great question. So one of the big things that we've been working on, and actually what we're going to have a short demo about, I thought it was after this, maybe not, is we've been working on like a dashboard where we expose a lot of the lower level primitives. So for example, one of the things that we plan to surface in the dashboard is like how many, like you can see how many tasks have been submitted, and we're hoping to show how many tasks like go through the fast and the slow paths. I think that would like, that doesn't quite get you all the way there, but I think it would like go a long ways to help. Yeah, that's a great question. Okay, thank you very much. So they're gonna